And today, my topic is about the interface engineering by the application of the tribology. So before that, I want to do a brief introduction about our previous and current project. Since 2020, tour group have invented the dual heating method, which is one type of the ultra-fast electron thermal method to prepare the turbostratic graphene. We start to use this method to chemically functionalize the graphene material by different heteroatoms to prepare the doped graphene. The doped graphene shows better electron catalytic performance. Then we expand this method to other nanomaterials like the boron nitride and carbides. Besides, we study the phase transition and phase evolution during this fast electron thermal process, and we found the formation of the metastable phase formation, like the transition metal dicogenase and carbides. Recently, our lab started to focus on using this electron thermal method to solve some environmental problems like the battery recycling and the electron waste recycling. On the other hand, we explore the surface modification of the polymer substrate and the metal foil using different methods like the laser coating method and the sanding method. And today we will focus on this part. The reason why we are so interested in the surface modification in different systems is because the interfacial property difference can determine the charge and material transfer during the interaction. As you can see from the scheme, when two materials are brought into contact with each other, the electron can be exchanged from the tribal positive to the tribal negative material. In this case, from the metal to the polymer because of the difference in electron negativity. And this is the principle for the tribal electron nanogenerator. In the electron chemical cell, the reduction and oxidation can happen for the electrode and electrolyte. And for the metal electrode, the surface property is related to the desorption and the deposition behavior of the metal. And these are very important starting topic for the rechargeable metal battery. Besides, the interfacial energy can control the facet of the nanoparticle during the growth. As you can see, the shape of the nanoparticle can be changed during this growth. In the high temperature solid state reaction, the interfacial property can also mediate the growth and the aggregation of the particle, like the Osterwald ribbon, which describe that the small particle can be merged into big particle during this annealing process. So today we will focus on the surface modification. At first, I will discuss how we can control the surface wettability by the sanding method. Then we will move to the metal foil and talk about the preparation of the artificial solid electrolyte interface by the surface sanding method. At last, I will talk about my own opinion about my title, the interface engineering and the application of the tribology. In case that you are not so familiar with the wettability, I will do a brief introduction. The wettability can be measured by the contact angle, and this is the angle formed by the liquid at the three-phase interface, where the liquid, gas, and solid intersect. Based on different contact angle, there are several different types, and if the liquid is water and the angle is less than 90 degrees, the surface is hydrophilic. And if this angle is larger than 90 degrees, the surface is hydrophobic. If the angle is further larger than 150 degrees, we call the surface is superhydrophobic. Different wettability have different applications. For the hydrophilic surface, since there's a strong affinity between the substrate and the water, it can be used for the water harvesting. And for the reaction in the aqueous solution, there will be a smaller polarization. For the superhydrophobic surface, the typical application includes the self-cleaning, the anti-icing, and the drag reduction. Followed by that, people start to found the self-adapting wettability, which means that the wettability can be directly changed from the hydrophilic to hydrophobic, or the opposite based on the stimuli, like the sunlight and the temperature. And this is very interesting for the microfluid device and smart coating material. However, there's still some problem about the preparation of this artificial interface with different wettability. As you can see, for the polymer coating, the coating mass can be directly decreased after the fabrication, and this can cause the decrease of the intrinsic wettability and performance. On the other hand, some superhydrophobic surfaces are prepared based on the nanostructure, and these nanostructures are very fragile with the abrasion objects. As a result, they have a poor mechanical stability. On the other hand, some methods involve the using of some reactive gas, as shown here, and multiple processing steps, which can be very problematic for the post-treatment. To solve the stability problem, different strategies have been tried. Like in the first case of the time stability, the stronger chemical bond can be used to link the coating material and the substrate. This can decrease the mass loss and improve the time stability. For the case of mechanical stability, the nanostructure can be combined with the stronger microstructure to form the hierarchical structure. This structure is much more resistive to the mechanical abrasion. Similar methods like the fabrication of the composite can be used to improve the stability of the material. On the other hand, the sacrificing layer with similar structure can be used. And after this sacrifice layer is consumed, more material can be used to replenish it. Followed by this method, I start to ask myself if it is possible for us to directly apply the material to modify the surface wettability with a good robustness. Luckily, I get some inspiration one day. In the morning, when my friend used a sunscreen, he sprayed it out on the surface, and by rubbing, it can form a very thin coating. So I wonder if it can be also applied to prepare the coating to solve my problem here. To make sure the material can be coated, we use a turbostratic material. So compare with the well-aligned material as shown here, like graphene with the AB stacking. The turbostratic material have a misaligned layer structure and weaker interaction, so it can be mechanical exfoliate. As you can see from the left side, we use the flash through heating method, which is a rapid high temperature electron thermal method. During the reaction, the temperature can reach more than 3000 Kelvin within 5 milliseconds with a very fast cooling rate, about 10 to the 4 Kelvin per second. Therefore, the individual layer of the graphene is not ready to align with each other. So we can kinetically control the formation of the turbostratic material. Then we did a simple test. We sandwiched the sample powder between two silicon wafers, and then we used a monodirectional mechanical force to exfoliate it. As you can see on the wafer, we can see the few layer material with the same edge shape as shown here. And this result indicates that the mechanical exfoliation can be used to coat the silicon wafer. So by adding the powder during the sanding process, we can prepare the homogeneous sanded surface. And as you can see from one example at the right side, the LIGF is one type of turbostratigraphene we use, and PTFE is polytetrafluoroethylene. Then we estimate the thickness of this surface coating. Also, we call this surface coating the tribal film, and the element content as shown here. So based on the change of the element, we can see the coating thickness is about 2 micron. We have tried different substrate, different sandpaper, and different additive in our sanding experiment to compare the result. For example, we at first try the 3 different substrates. Some of them, like polypropylene and high-density polyethylene, are slightly hydrophilic, and the polytetrafluoroethylene is slightly hydrophobic. And also, we try 2 different additive material. One is hydrophilic, and the other is hydrophobic. So when we use the hydrophobic powder to sand the surface, we can see the sanded surface can be superhydrophobic in this case. And when we use the hydrophilic powder, on the other hand, we can see the surface become more hydrophilic compared with the unsanded substrate. This result indicates that we can change the surface wettability in a large range based on different substrate and powder additive. So to further optimize the result, we test the effect of the sandpaper and based on the result of the contact angle. The contact angle in 220 is the largest in our case, as shown here. So this indicates that this type of sandpaper is the best for the fabrication of the superhydrophobic surface. Also, we change the additive, and we can see the contact angle can be changed in a large range from superhydrophobic to hydrophilic based on different additives, as shown here. Also, we change the type of the substrate we use to sand, and we can see from the contact angle, there's a little effect compared to the additive for the wettability of the sanded surface. Then we test the stability of the sanded surface, and as you can see, we measure the contact angle after different time after we fabricate the sanded surface. There's little change for the wettability after 18 months for different sanded surface, as you can see here. And also, we found that the same phenomenon for the thermal stability. We don't see obvious contact angle change after we heat the sample for 24 hours. And this result is reasonable since we know that the vapor pressure for the carbon is very low at the room temperature, and the thermal decomposition temperature of the carbon material is very high, at about 600 degrees Celsius. The Scotch tape test is to test the mechanical stability, and as we can see, after about 100 times Scotch tape exfoliation test, there's no obvious change for the contact angle, which indicates our material is mechanically stable. However, we indeed see that during the UV radiation, the contact angle of the surface can be gradually decreased. And this is related to the oxygen functionalization of the surface, which makes it more, which makes it more hydrophilic. So even when the temperature is as low as -40 degrees, the sanded surface can increase the time for water to freezing on the surface by 2.6 times, from 125 seconds to about 327 seconds. And it can also decrease ice adhesion strength for about 40%, as shown here. This indicates the sandy surface can also have very good anti-icing performance in our case. The other interesting phenomenon that we realize is that when suffering from the destructive abrasion damage, the resanding treatment can be used to fix it. As you can see in the middle side, after the abrasion, the substrate is exposed and the surface wettability degrades a lot. However, after we resand with the same powder additive, the surface wettability can be recovered as shown on the right side. And this result indicates that the tribal film itself can also act as a self-sacrificing layer and can be easily repelled by the resanding treatment. To figure out the morphology change after we did the sanding, the profilometer is used to check the surface roughness. As you can see in the micro scale, we can see the sanding treatment can modify the micro scale roughness. Then the atomic force microscopy is used to check the roughness in nanoscale. And the sanding material can contribute to the nanoscale roughness. So we modify the Cassiopacter model, and as you can see based on the graph here, we add the contribution from the microscale roughness and the nanoscale roughness as shown in the equation. If the F, the solid contact area, is 1, that means the surface is totally flat. And in our case, we have the surface roughness from the microscale and nanoscale. And the experimental data match good with the model, as you can see based on the two lines here. So this result means that the microscale and nanoscale morphology contribute to the surface wettability. So in conclusion for this part, the sanding method can be used to prepare the robust surface, and the turbostratic material are used to prepare this tribal film during the sanding. And this sanding surface is pretty stable based on our test, and the micro and nanoscale roughness are contribute to the wettability. Then we turn our focus to the metal foil by the sanding method. Due to the development of the portable electrical device, the people are pursuing, excuse me, the people are pursuing the rechargeable battery with higher energy density. To achieve this goal, the development of high-capacity electrodes is very important. As you can see, the current commercial battery are lithium-ion battery and then use graphite as the anode. The the specific capacity for the graphite is 372 million hour per gram. I'm sorry. If we can replace it with a metal electrode, the specific capacity can be greatly improved. For example, if the lithium metal can be used, The specific capacity of the lithium metal is more than 3,800 million hour per gram. This value is more than 10 times than that of graphite. However, this value can only be achieved without excess of the metal. Practically, it's very hard to control the electron deposition of this type of reactive metal. Here, we use the lithium metal as example. As you can see, due to the lattice mismatch between the current collector and the lithium metal, there is a large lattice mismatch, and it causes the nucleation of potential and induce a formation of the nuclides as shown here. This can further induce the formation of the dendritic structure because of the heterogeneous electric field, ionic flux, and so on. This dendritic structure has some safety concern once it breaches the anode and cathode, and this will cause a short circuit and thermal runaway. On the other hand, this dendritic structure cannot be 100% utilized. This can cause the low efficiency and this isolated lithium formation. Besides, the non-uniform growth of the lithium metal and the large volume expansion during the cycling can cause a fracturing and reforming of the protective layer. This is the solid electrolyte interface, SEI, as shown here. The repeating of this process can cause the SEI accumulation and polarization buildup. So to better control this metal electron deposition, we should know how it works. Generally, there are 4 associated stages. At first, the solvated metal cation move from the bulk solution to the liquid-solid interface, and they are reduced at the interface. This reduced atom further causes the heterogeneous nucleation of the metallic embryos, and at last, the metal starts to grow. Previous studies have shown that as the O potential increases, the nucleation density can also increase and the size of nuclei decrease. This can be explained by the free energy change, as you can see here. Therefore, the Gibbs free energy of the nucleation and interfacial free energy of the electrode are essential to control the nucleation and metal deposition. And indeed, most of the work on lithium metal anode is based on the modification of the metal electron deposition. For example, replacing the 2D metal foil with 3D metal mesh, since the 3D structure have larger surface area, which can average out the total applied current and minimize the local current density. This can reduce the polarization and improve the deposition. Also, the electrode, which can form the alloy with the deposit metal and the new electrolyte, can be used to improve the metal deposition. Besides, the other common one is to pre-treat the metal electrode with some additives, especially the fluorinated compound. An artificial protective layer can form, and this layer will regulate the incoming lithium metal deposition. Many different types of the additive have been used, like the polar salt, like the lithium nitride, organic compound, and other non-polar compound. However, the polarity, reactivity, and solubility may limit their ability to be introduced as an additive. So we want a direct method to introduce this additive for us. So in this part, we first want to develop a general method to introduce the additive for the electrode modification. And then we want to study the electrochemical performance of the modified electrode. At last, we want to explore what happened at the interface of this modified electrode. As you can see from the scheme, we propose the solid brushing method to coat the metal electrode by using the fine powder as the additive. At first, the surface is scrubbed with a brush to expose the fresh lithium. Then the metal powder can be sprinkled on the surface, and it is rubbed against the surface to form the coating. This process is similar what we we are doing the oil painting on the paper. Based on our method, the homogeneous coating can be achieved by repeating this process for twice. The optical imaging for several powder modified electrodes can be seen here, and some of them are homogeneous. After the modification, we use the electron chemical performance to screen the powder. And here we use 4 different performance indicators, including the onset of potential, which is the lowest of potential during the initial cycling as shown here. Then the potential will gradually increase to the steady of potential. And the difference between the steady of potential and onset of potential is the nucleation of potential. And this indicates the polarization for the nucleation. At last, the voltage profile of the symmetric cell from the initial 150 cycle is used to compare the performance. And the current density we use here is about 1.0 million hour per square centimeter with an area capacity of 1.0 million hour per square centimeter. So as you can see, based on the all potential at 0.1 million hour per square centimeter, which is a very low current density, and 1.0 million per square centimeter, which is practical current density as shown here. Compared with bare lithium, the molybdenum disulfide coated lithium and P2S5 coated lithium shows a lower nucleation of potential at both current density as shown here. And polyacyl nitrile only shows a smaller nucleation of potential at a low current density, which indicates the limit mediation performance. However, for the other type of the powder like PTFE and also the brushed lithium without powder, we can see a larger of potential as shown here. Also, on the right side, we compare the onset of potential and steady of potential, similar as what we see from nucleation of potential. At this low current density, P2S5 and MOS2 shows a lower of potential compared with bare lithium. Therefore, P2S5 and MOS2 can modify the incoming lithium deposition. Then we compare the voltage profile of these several different types of the sanded lithium electrode, as you can see from the curve. So during charging, if the voltage is larger, this means the polarization is larger. And during the discharging, if this voltage is lower, that means the polarization is larger. So by comparing the voltage during charging and discharging, we can see similar phenomena like MOS2 and P2S5 can lower the voltage during charging and increase the voltage during discharging. And these two materials also show more stable voltage profile compared with the bare lithium and other coating as shown here. With all these previous screening results, the long-time stability test is shown here. So we compare the P2S5 coated lithium and bare lithium. For the P2S5 coated lithium, it shows a stable voltage profile for about 4,000 hours in the symmetric cell as shown here. However, under the same condition, there's a larger potential for the Bell lithium, and after about 500 hours, the polarization starts to build up rapidly, which means the fail of the cell. And in the full cell test with the lithium iron phosphate as a cathode, which is a very common cathode, we use a practical area capacity about 3.2 million hour per square centimeter. We can see after about 300 cycles, the capacity retention for the cell with P2S5 coated lithium is about 80% higher compared with the Bell lithium in our test condition. So to figure out the reason for this performance difference, we characterize the morphology change of the electrode after different stages, include the lithium stripping followed by planting, lithium planting, and lithium planting followed by stripping. And as you can see from the imaging, for the Bell lithium, the pits start to form after the lithium stripping, and we can see the deposit after the stripping followed by planting. On compression, there is a more homogeneous surface morphology after stripping and planting for the P2S5 coated lithium. Since the morphology difference is caused by the different behavior, we build the transparent cell to monitor the growth of the lithium metal. The voltage profile can be first seen at the right side. For the Bell lithium, at this condition, we can see a large onset of potential, and after about 1 hour, we can see the voltage suddenly go to 0, which indicates the short circuit of the cell. However, for the P2S5 coated lithium, there is a much smaller potential compared with the Bell lithium, and there's no short circuit happen for the cell. Based on the imaging shown in different stages, we can see for the Bell lithium electrode, we can see the inhomogeneous lithium deposit as shown here. And at last, it caused the breach of the two electrodes and caused the short circuit as we see in the voltage profile. However, for the P2S5 coated lithium, there's a much more homogeneous lithium deposition behavior as shown here, and at last, it's still pretty homogeneous. And during the subsequent, the next desorption process, this lithium can also be dissolved with a homogeneous behavior. Then we characterize how this surface coating play in this artificial solid electrolyte interface. And for the P2S5 itself, we can see a series of sharp peaks as shown on the left side. However, after we set the powder with the lithium metal, we can see the formation of the different types of thiol phosphate. This is the product between the reaction between the P2S5 and the lithium. And this thiol phosphate have a large ionic conductivity and large bulk modulus. This character can guarantee the stable and more homogeneous lithium deposition behavior during the cycling. And we also observe the similar lithiation behavior of the MOS2, PTFE, and PANI. So for this part, we use the solvent-free brushing method to introduce a powder additive on the different metal electrode. We saw the spontaneous reaction, basically the lithiation of the surface coating, because the lithium is very reactive. And this is very important for the electrochemical performance. And we characterize the morphology change of an electrode and observe the different lithium deposition and stripping behavior. At last, I want to talk about my own opinion about interfacial engineering and application of the tribology. So we know during the sanding procedure, the force can be expressed as the equation shown here. The F is the pressure and the mu is the friction coefficient. The local force can be dependent on the contact with the microstructure and nanostructure. And there are different forces in different scale. And this figure, the figure shown here, this and in my PhD, this is my favorite figure here. So we can see there are different forces like the thermal energy force, the mechanical force, and even the binding energy. So this force have different range in different length scale. So we have a chance to make the change and achieve the desired nano mechanical reaction and the surface function based on this relationship. And on the other hand, for the interfacial engineering part, I think based on my field, there are still several problems that might be solved by this sanding method. One problem is the interfacial contact, especially in the new solid-state battery. The connection between the electrode and electrolyte. The solid electrolyte is always a problem. Maybe by using this sanding method, we can solve the contact problem by forming a stable layer. And the other thing is we have shown that we can use the sanding method to functionalize the lithium metal anode to protect it with which can guarantee the improved performance. We can still search better additive to get better performance in this case. The second field, I think this can be used in the interfacial activity, especially for catalyst. If we combine with some mechanical process, the interfacial activity can also be boosted. And the third thing is that this can also be used to functionalize the interface, achieve other functionalization in different fields like bio and other fields. At last, I'd like to thank you, my group, my supervisor, James Toole, and the lab manager, Dustin and Carter, also the postdoc who guided me through the project, and my friend, John Lee, who helped me with all this project, and Zui, who guided me all these several years, and other lab mates, and also my collaborator from Professor Heath's group, Victoria. So I also want to thank you, the funding source I've listed here, and the arrangement of this presentation, the CPS staff and everyone who is here today. And I'm very happy to take any question now. Thank you.
Thank you so much. That was super interesting. So if anyone's got any questions, feel free to just unmute yourself and ask it, or you could just type it in the chat as well. If not, then I do have a question myself. So I was just curious that over time, how will the the effect of this sort of this addition to a surface? How will it decrease? Like, will the surface wettability change like over time?
Over time, I think you mean the polymer or the metal foil part for the stability? No?
For the polymer.
Oh, for the polymer. In fact, we indeed tested the solubility as shown here. After 1 day, 1 week, 1 month, and 18 months. In fact, the thing that we see is based on the contact angle test, there's no obvious change. But, you know, we store the sample inside the Petri dish. So if we expose this directly in air, the dust on the air might deposit on the surface. And we also have noticed that, then that might affect your wettability. But if you avoid the dust deposition and put them into the Petri dish, I think during a long period of time, there's no obvious change of the wettability because we use a carbon material as the additive, which is very stable based on the ambient condition.
I see. Thank you very much. There's a question in the chat.
Could you prepare different shape? Oh, could we prepare different shape? Oh, that's a great question. For the slide we list here, we do the coin cell test, which is a circle, the electrolyte circle. But in fact, when we at first do the standing of the metal foil, we use a very large metal foil. And after we modify the whole surface, we can cut the big foil to different shape based on our design, like in the pouch cell, which might be a rectangle shape. We have also tried that, like this. So in fact, the shape is not a problem. Just we need to cut a very big, prepare a very big standard metal foil and cut to the shape that we design. It should be fine.
And then I think Sophia has her hand up.
Yeah, hiya. By the way, just really good talk. I really enjoyed it. I've also just to clarify, so did you, for your superhydrophobic surfaces experiments, did you do it on glass, or what actual surface did you do it in? I didn't catch that bit.
Oh, I'm sorry. I go that part very fast. And at this part, we try several different polymer surface, in fact,
Okay.
including the polytetrafluoroethylene, polypropylene, high density polyethylene, polystyrene, and polyvinyl chloride. These 5 types are thermoplastic polymer and PDMS, polydimethyl. Yeah, this is a polystat polymer. So we have indeed tried to use metal to do the same thing here, but we might need to change the sandpaper to other material because the strength of the sandpaper we used might be not good enough. And also for the case of the glass, we think by changing different sanding paper like silicon carbide, we can use the similar method to functionalize the glass too. But that can be a good experiment to do if you can modify the glass too.
Oh, okay. Yeah, because at the moment I'm trying to do super hydrophobic surfaces on a cotton, like on textile. Do you think this making it more robust on a textile with this sandpaper method, do you think that's a possibility?
I think it might depend on what's the material, what's the exact material of your code.
So
You
just
want
for
to,
example, but like for example, polyester textile, let's say.
that's a very interesting experiment that you can try because that's also one type of polymer. And in fact, currently we are thinking how to transfer this technique from the flat surface to the curved surface.
Yeah.
In your case, the fiber texture, it can be a good start point. Like you can use some substrate at the back side to support your material, and you use the sandpaper to sand on the surface. And this can work to achieve the surface functionalization in my mind.
Okay, interesting. Thank you
If
so
you want to
much.
try that, just, you know,
Yeah.
let me know.
So
Maybe you can get good news.
yeah, I'll let you know. So you're saying kind of, so it would be good to put a substrate to support you know, that surface, the textile, and then do the sandpaper on it.
Yeah, because when you apply the force to your material, you must need to put something at the backside. Otherwise, if your material is kind of soft, it will deform and cause kind of the inhomogeneous coating, or that might be not good for your application. We want a more homogeneous coating, right? So that's why I think use a very flat surface at the backside to support it. It can make sure you get homogeneous coating.
Yeah. And what was the sorry, I'm asking so many questions. What was the technique that you used to actually put the thing on? So you know how there's like aerosol deposition, there's like dipping. Is this a whole technique in itself, or?
Yeah, in fact we don't use the aerogel or any liquid. So the reason we directly use the solvent-free, a very dry method, we just put the powder on the surface and use sandpaper to sand. And the reason why we can achieve this is because, as you can see from the graph here, we can put the powder between two silicon wafer, and we can apply the monodirectional mechanical force to exfoliate the material to thin layer coat on the surface. This material that we use is turbostratic graphene. So this we use this type material because it have a weak interlayer interaction, so we can easily exfoliate it to form the coating. So that's the reason why we can directly use this dry method to coat with this. We also, in fact, try the normal graphite, but using the similar method, it's hard for you to exfoliate it, as we can see based on this turbostratic material as shown here.
Okay. Yeah, interesting. Thank you so much.
Thank you.
Thank you.
Any more questions at all? If not, then I just want to say another big thank you for coming and speaking for us today. It was really extremely interesting, and I'm sure everyone really appreciates it. So yeah, thanks everyone for coming, and I hope you have a great rest of your evening.
Also, I was just gonna ask, what is your email?
My email is
Sophia, I can put you in contact if you like. I can give it over for you.
Yeah, that would
That might be
really,
might be easier, yeah.
yeah, that would be really helpful.
Of course, yeah.
Yeah.
Perfect. So yeah, thanks for coming everyone. Have a lovely rest of your evening, and hope to see you at the next talk.
Thank you so much.
Thank you.
Lol.
Hey. I was like, I'm not sure if I should speak to him and just say like a little private thank you at the end.
Yeah.
But he just left, so I was like, fair enough, see ya.
Oh, yeah.
It's like-
What is his email?
Oh, wait, hold on. I can't get it to you right now. Wait, shall I get to Polly over as well? Polly. Polly. Do you want to say hi to Sophia? Oh my God. Oh. Yeah, just in management.
It was pretty good. Well,
It was really good, yeah.
to be fair, for me it was brilliant because this is
Yeah,
this is what
yeah,
I
like
do.
at the end when you were like, this is what I'm researching, I was like, damn.
I was like, this is great. Like, because I didn't even know about that technique. I've never even heard of it. So no, very cool.
That's
Very
good.
cool. You know. How are you?
Good vibes from this one. I'm okay, how are you?
Yeah, fine. Just, you see it.
Good. Wait, so if you're researching this, does that mean you're in your master's now?
Yeah. Mm-hmm.
OMG.
Yeah.
So
I know.
crazy.
I know. It is pretty cray. I mean, honestly, like it's intense, but we move.
Is it?
Yeah, it's intense. No, but honestly, like I can't do anything about it. Like you just have to deal with it. You know, you just have to deal. Also, actually,
you're like interesting. You were like researching interesting.
yeah.
Oh, that's fine. Are you going in a bit?
Hello. How are you? Yeah. Yeah, pretty good. The talk was really good. Not gonna lie. Also, I think I can actually get his email by looking at the schedule.
I have just forwarded you the chain because I'm too lazy to copy the email.
Yeah, no, that's fine.
But yeah, I'm enjoying the conversation that I had with him earlier.
I love that. Enjoy. Wait, so
Yeah,
do you just send me the chain of everything?
I either sent you a chain or I sent you like the most recent email. I'm not really sure if I'm honest, but there's no privacy issue on that. It's just the GDPR form. So
yeah, no, that's fine. That's fine. Did you do Sophia.Ruiz?
went well, guys. I'm gonna head to Shein Centre to eat my dinner and then probably work in there.
Yeah. Did you send it to Sophia.Ruiz? Or
I sent it to your UCL email.
yeah, I know there's another Sophia around, so like Sophia.
Oh no, I'm pretty sure it's yours because the profile picture on it.
It's me. Okay. Oh yeah, it's here. It's here.
Did you get it? Awesome.
Yeah, I got it. All right. Thank you so much.
Thank you. Thank you guys for
I will
coming.
see you guys soon.
Wait, are you coming to the IOE?
IOE?
Yeah. I thought Tina said that.
Oh right. Yes, I am. I was like, what? Is this an actual event? Like, is it like because I was like, is this an actual event? No. Yeah, I am. We're going right now, actually. Yeah, we're going now. So are you coming?
Yeah.
Okay, then I'll see you there. Bye.
Yeah.
Bye. See ya. Bye. Bye.
Bye. Bye.